Hi everyone, it's me, Carolyn, and in this video we will be talking about some testing of categorical data. So we'll be seeing them put in like contingency tables in tables. And we saw those a little bit in chapter 5 when we were talking about probability. So without any more wasting of time, we're going to start with our guided notes and kind of walk through the steps that need to be done. And I do have two examples that we're going to go through. So first of all, the first type that we're going to do is test for independence or homogeneity of proportions. So in other words, trying to determine if we have two variables, if they are related or not. So talking about independence, is there a relationship between them? And the second one is testing to see if proportions, if we have a yes-no situation and we're testing a bunch of different things, if those proportions are consistent or the same throughout all of those pieces. So the chi-squared test, so we'll be using a chi-squared again. However, we'll be using a different way of entering our data into StatCrunch because these are in table format, so it's a little bit more complicated. Still not difficult in StatCrunch, but just a little bit more things to remember. And it is a chi-squared, so we've talked about the chi-squared curve in 12.1. And we will be, the first one we're going to do is determine if there's a relationship or an association between our row variable and our column variable. Now, these tables could be large or small. The examples I have are kind of smaller on this side, being a little bit smaller. But again, we're going to be doing a 5-step test. And our null hypothesis is always going to be that they are related somehow. Okay, or they're not related, sorry, that they're independent, that they're not related. So they're not associated with the other. The alternative is that there is some sort of connection. Now, we won't be able to determine what that connection is exactly, but all we can say is that there is some sort of association, some sort of dependence. So there's our step 1 is those hypotheses. Step 2 is to find, of course, that alpha level. A lot of times that is stated in our problem. So we just have to find it. Our requirements are very similar to those from before, that all of our expected frequencies are greater than 1. Our expected frequencies are found a little bit differently. So we have to kind of go through this piece here. I will go through one to show you. Once I go through the entire test, I'll come back and we'll go through how to find that expected frequency. I use StatCrunch on these because the calculations to do by hand are very tedious. We also want to make sure that no more than 20% of our expected values or frequencies are less than that 5%. Our test statistic is the same as we've seen before. We take those observed values minus those expected values, subtract those, square them, divide by that expected, and then add all those pieces up. Since we have many, or could have lots and lots of pieces in our table, we may have quite a few that we need to add up. Step 4, of course, is finding that critical value using our chi-squared table, or we could find that p-value, which will be given to us in StatCrunch. Again, I will show you how to do both just so we have them. And then again, we would make our decision. And of course, always making sure to write that conclusion in layman's terms as if they knew none of the background. So like, you might set up the experiment for a person, like tell them what we were doing, what we were testing, but all of these steps 1 through 4 and part of 5 usually aren't going to be stated in our publications or things like that. We usually just kind of write our conclusions. We may include the p-value that we got, but again, we want to write the conclusions as if they didn't see some of the setup. Excuse me. So we're going to look at our first one. Okay, and we're going to say, are health and happiness related? So kind of look at this guy up here. So I'll kind of cover the rest of this up so I can bring him up a little bit. And we have some data. So what basically we kind of would give people a table and say, okay, on the health scale, are you in excellent health, good health, fair health, or poor health? And then again, how happy are you? Are you very happy, pretty happy, or not too happy? And we want to ask, is there a relationship between your health and your happiness? And we're going to do at 0.01. Okay, so I'm going to go through my 5 steps. Again, I am going to use StatCrunch to help me quite a bit. But again, I'll come back and show you how to get those expected values on a couple of examples, just kind of set it up for you. I'm not actually going to do it, but I will set them up for you. So step 1 is to write those hypotheses. And we always say, start with health and happiness are independent, meaning not related to each other. One doesn't affect the other whatsoever, versus that they are somehow related to each other or connected, are dependent. So independent and dependent are pretty statistical terms. If you were talking to someone in the street, I would probably use that they're related or not related, or they affect each other or don't affect each other. Okay. Our step 2 is at alpha level. We were using alpha to be 0.01. And step 3 is our test statistic, which I'll get from StatCrunch. Step 4 is our critical value, which I'll get before we go to StatCrunch, but I'll also get our p-value from StatCrunch. And then step 5 is to make our conclusion and so forth. Now, again, we are using the chi-squared. And I did go very quickly over the degrees of freedom on the previous sheet. But the degrees of freedom is going to be our C minus 1 times our R minus 1. C being columns and our R being the number of rows that we have. So if we look at our table, okay, we have 1, 2, 3 rows. Oops, sorry. 1, 2, 3 rows, and we have 1, 2, 3, 4 columns. So 4 minus 1 times 3 minus 1, which is 3 times 2, or 6. Okay, and we were doing an alpha of 0.01. So again, here is my chi-squared table. And so we have 6 degrees of freedom. Our 0.01 is way over, and we have 16.812. So our critical value is 16.812. All right, I am going to go to StatCrunch now and get all of the other information that I can. Again, I did previously put in all of this information here. I did label happiness at the top, and I kind of put the pieces here. I didn't write them all out. Very happy, pretty happy, or not too happy. I just left out the happy word. Our excellent, our good, our fair, and our poor. Now we do have a table thing. We're still going to go into stats, but since we're talking about a table, we're going to go to these tables. Tables that are kind of laid this way that have people in each category is a contingency table. I do not have the raw data. Like I don't have like someone telling me their happiness and then someone telling me their health. So it doesn't have to match it all up. I've already matched everybody up and put them in the categories. So we do have the summary. Okay. So that 271 that was sitting there is the summary that there were 271 people that were very happy in excellent health. All right, so I'm going to select my columns. Now I do need to select all of them. So my excellent, my good, my fair, and my poor. So I'm going to actually collect all of those. I'm clicking and dragging, so not all of them. I just want those 4. Excellent, good, fair, and poor. my row labels, because I did label. Those are my happiness ones. Those are right in here. So I have my very pretty and not too. I can label my columns. So if you remember, our columns were the health that we had. I'm going to put that in there, and I type that in directly. The last thing I really need to worry about is this confidence level to make sure that I get the right pieces. And we had a 0.01. I don't think this is actually going to matter, to be honest, because we get our p-value and our test value. So you really don't need to change that, I guess. Sorry about that. And I'm not going to show the graph just because that's more extra work. So now I'm going to compute. So here we are. Okay. I'm also going to, while I'm here, because I do need these totals to calculate those expected. And I wanted to show you how to calculate some expected. So 634, 1098, 264. We have a grand total of 1996, 551, 931, 109. Okay. Here down in the bottom piece, we do have our value. That is our step 3. So our test statistic, adding up all of those pieces, is 182.17, and our p-value is smaller than 0.0001. So very, very tiny p-value. All right, I'm going to get rid of this so when I come back to do my second example, we can go right to it. I am going to go back to our guided notes so that I have all of our pieces here. Let it refresh. Okay, I'm going to finish our conclusion here so then I can go back up to my table and show you how to find some of those expected pieces. All right, so we have our test statistic, we have our critical value, and we have our p-value. So we are all ready to make our decision and write a conclusion. So if I were making a decision based on the test value with that critical value, remembering our chi-squared is some sort of curve that starts at 0-ish and goes just to the right. Our critical value here was a 16,812. That sets up our kind of our rejection region or our critical region. We place that 182.17 in here, which is going to be somewhere here. So it is in the rejection region. Yes, in the rejection or critical region, however you want to label it. I'm not sure everyone labels them that way. I usually do. Just helps me remember when I reject and not reject. My p-value, we kind of look at what we want to do is it smaller than the alpha level of 0.01? And this is smaller than this, which of course is smaller than that. So yes, it is smaller. So we will be rejecting. Okay, and all of this is nice and handy and stuff like that. But when it comes to publishing or letting someone non-statistical understand what we just found, is we would tell them that there is significant, I can't spell that, substantial, that's maybe a better word, evidence to show that happiness or a person's happiness is dependent on their health. Or maybe that kind of sounds backwards, because I don't know if their health is dependent on the happiness or that a person's happiness and health are related. That might be a better way of saying it. Okay, because it's not really telling us, we don't know if happiness is dependent on your health or if our health is dependent on our happiness. All we know, all we have shown is that there's a relationship between the two. They are somewhat related, somehow related. How they're related, that we have not looked into. That would require further study. Okay, I'm going to go back up to our table. I wanted to show you how you would find an expected number. And if we had to do this by hand, we would have to do this for all of these pieces. So we'd have to do this for all 12 spots. So I'm just going to do this expected up in this very first column. So I'm going to call this column number 1. So our expected, finding what we should expect in that column if these pieces were completely independent from one another. I'm going to kind of remind you the formula for our expected. It's going to be that row total multiplied by the column total and then divided by the table total. Okay, so for this piece here, our row total was 639, or 634, sorry. Our column total was at 551, and we're going to divide it by that 1996. And so getting my calculator, 634 multiplied by 551, and then divided by 1996 is 175.017, and there are more digits. Okay, so we would have to do this for every single piece. Okay, and then when we go to calculate our test statistic, we take this 271 minus this 175.017. We have to square it and then divide by the 175.017 and get those values. And we have to do this for all 12 little cells. Okay, hence the reason technology has saved us so much grunt work. And it just is it's a lifesaver in the statistical world when computers came around, because statistics is an application of mathematics. I mean, we are doing math, we're doing some arithmetic and math. And the math that we do, the arithmetic we do, is very long and tedious if we did it by hand. So it is a nice, very nice thing to have all of these wonderful technology tools. Okay, let's go on to another example, because what we did is we kind of tested to see if things were independent or not. If we're looking for homogeneity of proportions, basically finding out if more than 2, because we've tested 2 before, but we're going to test more than 2, whether or not we have the same proportion for these characteristics. Okay. Step 1 is slightly different because we're going to be testing to see if proportion 1 is equal to proportion 2 is equal to proportion 3, on to however many we have. Okay, we will have a finite number. It's not going to go on forever, but we will stop at some point. Versus at least one of them is different. This test does not tell us which one is different, but it does tell us that one of them is different. Steps 2 through 5 are exactly the same as if we were doing independence. So the only thing that changes is how we write our hypotheses. All right, so here's my example that we're going to work through. And we have clinical trials. And what they're doing is trying to determine whether or not these medications that people are on cause dizziness or not dizziness, if it differs between the different drugs. Okay, and so here we have Celebrex. We have some sort of placebo, which is a fake drug. We have naproxen. We have, I don't even know how to pronounce this, but I'm going to go with diclofenac. And then we have ibuprofen. And these, again, are summarized. If we had the raw data, we'd have someone that said Celebrex, and we'd have them saying no dizziness. Celebrex and dizziness. We have combined all that information into this table. So we've already done the summary. And we put all the people in, whether or not they have dizziness or no dizziness. And we want to go through and find out if there is a difference in the proportion of people who suffer from dizziness or the proportion of people who don't suffer. Can think of it either way at an alpha level of 0.05. Okay, so I'm going to go through my 5 steps. Again, I am going to use StatCrunch to save me all of the work that I possibly can. So step 1 is writing those hypotheses. I am going to use some little somewhat notation. So we want to know the proportion of Celebrex is equal to the proportion of the placebo, equal to the proportion of the naproxen, equal to the proportion of that drug, equal to the proportion of ibuprofen. I probably should capitalize that. So we're wondering, are all of those proportions the same, or at least one of these proportions are different? Okay. Our alpha level that we have is 0.05. We're going to need our test statistic, which is a chi-squared, that we're going to get from StatCrunch. Step 4 is our critical value, or our p-value, which we'll get from StatCrunch. And then step 5 is to make our conclusion. Okay, I'm going to get our critical value before I go to StatCrunch, get that off of our table. Our degrees of freedom, again, equal to the columns -1 times the row -1. Columns, we had, find my table, 1, 2, 3, 4, 5 columns. And we only have 2 rows. So we have a degrees of freedom equal to 4. Okay, and our alpha level is 0.05 that I needed for here. Critical 4, and we're going to 0.05, so 9.488. 9.488. All right, and now I will go to StatCrunch for the rest of it. So I'm going to be getting my test statistic and my p-value from that point. I do have to do all the rest of it myself. You know, make that decision. I have to do the thinking part of it. Okay, hopefully I have StatCrunch being shown. Make sure. Sorry, don't think you were looking at StatCrunch. You should be seeing StatCrunch now. Yeah. All right, and I did put all of that information over here. So here's my side effect. We have the dizzy or not dizzy. Here are the 1, 2, 3, 4, 5 different drugs that we have. Again, to do the statistics in StatCrunch, we do have it in table format. This is a contingency table. And again, with the summary, because I don't have all the raw data, we've kind of grouped them already, so we don't have to worry about doing that. Okay, and we did this one in the last one. So here we have our Celebrex, placebo, all the way down to ibuprofen. So our 1, 2, 3, 4, 5 different drugs. Our row labels are in the side effect. Okay, my column label, I'm going to label it as drug name. Okay, and I am ready to compute. Oh, and I put the graph on here. Not that we needed the graph, but all right. So you'll notice here we have the totals again. So if I wanted to do it by hand, it could get those expected values. And it wouldn't be a bad idea to double check some of these expected values to make sure that they are all bigger than 1. And make sure that 20%, at least no more than 20% are smaller than 5. There was our degrees of freedom. Again, is that 4 that we came up with. There is our test value, that 4.67, and I'll just put 3. And our p-value is 0.3226. All right, so there's all the information I need. So I'm going to go back to our guided notes. and let it refresh here for a moment. There we are. So there's our test statistic. Here's our p-value. Again, depending on how you wanted to make your decision, if you were looking at the picture, the critical value sets up the critical region. And our test value, we want to kind of figure out, where does our test value fall? It is right here. It is not in the critical region. I'm going to abbreviate that critical region. Okay, here we are checking to see, is that p-value smaller than our alpha, which is 0.05 in this particular case. That is also a no. That is not true. So we will not reject. Okay, which means there is not enough evidence to show a difference in the proportion of, I'm just going to say patients, patients who suffered dizziness to show a difference in the proportion of patients who suffered from in these different drugs. And this is not something I am good at, is writing these things. I am a statistician. I am a mathematician. English is not my strong suit. So writing those sentences is not something I'm great at. So I'm sure it could be critiqued a little bit and smoothed out a little bit. But basically, we aren't seeing any difference between the different drugs. So I am going to stop sharing, because we have gone through the two examples that I kind of wanted to do, and we kind of walked through everything for chapter 12. Again, we're just getting touches on some of these pieces, and I'm hoping that you can see some of the different things that happen out in the statistical world, and what and I mean, these technologies have not been around for a very long time. So I want to say they've been coming around in the last 5 to 6 years. So before that, just imagine the work that some of these people were doing, mathematically speaking, all of that grunt work to get those test statistics and things like that. So amazing things what technology has done for us over the years. But with that, I'm going to say have a great day, and I will see you in the next video.